In this lecture, I will first discuss the difference between the fixed effect model and first difference model, and then I will discuss the estimation of random effect model, and then discuss the possible tests to decide whether to use pool model vis-a-vis the panel model, and then discuss the Houseman specification test to judge the applicability of fixed effect or random effect model. And then I will discuss the different approaches used for the estimation of the panel model. In the last class, I have introduced the panel data method, and I have also introduced the fixed effect model and first difference model. Now, let us make a distinction between the fixed effect and first difference model. Now, for t equal to 2, two methods are identical. For t greater than or equal to 3, the methods give rise different result, but given the assumption both are unbiased and consistent for short period, you get that as t is fixed in tends to infinity, the we have a case of unbiased and consistent estimator. Now, for long period, that is t larger than 30 say and n not large, co-integration problem may be present in the data set. So, here fixed difference for the first difference method should be safer, because first differencing will eliminate the time frame present in the data set and thus remove the co-integration problem. So, for some of the cases there is the possibility of using first difference method, because in the data set you may avoid the co-integration problem. Now, estimation of fixed effect model based on unbalanced panel data set does not pose much of the problem. Now, one of the basic assumption of panel data set is that for n cross sectional unit of the panel, it constitutes a simple random sample from the universe of such unit, and missing unit for some times may make the sample non-representative. The data set may get affected by selectivity bias, which may make the estimates inconsistent. So, you may end up with a situation of selectivity bias, and that may result inconsistent estimate of the parameter. Now, come to the random effect model and its estimation procedure. Now, write the model as yit equal to beta naught plus beta 1 x 1 t plus ai plus epsilon I t, I equal to 1 to up to n and t running from 1 to capital T. Now, the assumptions are AIs are random drawing from a distribution having expectation of A equal to 0 and a given variance. Strict endogeneity of AIs, that is x's are assumed, that is expectation of AI given x's are equal to 0, and homoscedasticity of AIs, that is variance of AI given x's are sigma s square for all I running from up to n, and also note that expectation of AIA equal to 0, the intercept term B naught will capture the non-zero mean level of the Y data. Now, random effect model assumptions 11 implies covariance of xit ait equal to 0. Therefore, for the random effect model, OLS regression of y on x based on the pool data set will give the unbiased and consistent estimate of the parameter beta naught and beta 1. But these estimates are different from the corresponding random effect estimate. Now, in order to visualize the random effect estimation process, let us first note that the composite error term VIT equal to AI plus epsilon IT of the equation 10 is necessarily autocorrelated because V1t up to V2t are present not for every I. The correlation between VIT and epsilon IT are given by VITS and covariance between VITS and VIES is equal to sigma s square divided by sigma s square plus sigma epsilon square for r not equal to s. Now, the positive autocorrelation of the error which can be substantial is taken care of the random effect estimation by the following transformation of the random effect model. That is, in order to avoid the problem of correlation between VITS and VITS between two that is the error term at two time point, a suitable transformation is made following and YIT minus lambda yi equal to beta naught plus 1 minus lambda plus beta 1 multiplied by xit minus lambda x bar t plus VIT minus lambda VIT. Note that this random effect transformation and the fixed effect transformation are very similar looks like. Random effect transformation will allow time constant variables like dummies for the cross sectional unit in regression equation, and lambda is not known, an estimate of lambda hat has to be obtained, and this is done by using residual obtained from the pooled OLS of the fixed effect estimation. Now, if xit and A are correlated, then random effect estimator of the regression coefficient will be inconsistent. And OLS estimation of equation 13, which is the GLS estimation of equation 10 using the appropriate variance covariance matrix will give us the random effect estimation. So, random effect estimation is basically is the generalized least square estimate of the original data model, allowing for the existence of appropriate variance covariance matrix of the composite error term. Now, under the random effect model, assumption of this will be under the assumption of random effect model, this will be unbiased, consistent and efficient. So, GLS estimation of equation 10 will provide us the unbiased, consistent as well as efficient estimate of the structural parameters. Now, let us examine how we should distinguish between fixed effect model or random effect model. That is there any test to examine whether we should use fixed effect model or random effect model? The test that examine whether data set will contain all the observed component, assuming GDP is coming from the random effect model, is given by YIT equal to beta naught plus beta 1 xit plus alpha I plus epsilon it, and the null hypothesis sigma s square equal to 0 is tested, and if H naught is rejected, the panel OLS will be consistent. So, if we find that H naught sigma s square equal to 0 is not rejected, and then panel OLS will be consistent. Now, the Bruce-Pagan Lagrange multiplier test is used for this purpose. The random effect model is estimated, and then using the random effect regression residual, an analysis of variance is performed to check if the variance component due to unit I is statistically significant. Now, if H naught is not rejected, panel OLS will be consistent and may be efficient. Now, rejection of H naught indicates the presence of unobserved effect component, and the nature of the unobserved effect component, fixed effect or random effect type, to be determined next. So, if we find that pooled model is not the appropriate one, then next question is whether to use fixed effect model or random effect model. That will be decided on the basis of the next test. So, test of the random effect assumption, and this is basically done by Hausman test. Now, if true DDP is random effect model, both the random effect and fixed effect estimator of the regression coefficient will be consistent. If on the other hand true DDP is of the fixed effect one, fixed effect estimator of the regression coefficient will be consistent, whereas the corresponding random effect estimator will not be. So, Hausman test of random effect assumption test H naught, true DGP is random effect model. Now, suppose random effect suppose beta hat Fe and beta hat Re are the fixed effect and random effect parameter estimate and are their estimated asymptotic variance covariance matrix. The Hausmann test statistics is given by H is the difference between beta hat Fe and beta hat Re multiplied by variance estimated variance covariance matrix of the fixed effect and random effect estimator and inverse of that and multiplied by beta hat Fe and beta hat Re. Now, under H naught Re model assumption holds and this follows a chi-square k distribution. Note, the Hausmann test will help to decide whether random effect to be accepted against fixed effect or not. Researchers often choose between random effect and fixed effect based on whether AIs are the best viewed as parameter to be estimated or outcomes of a random variable. So, in the fixed effect model we treat Aij as parameters and in the random effect model we treat Aijs are basically coming from a random sample of a suitable purpose. Now, when cross sectional units are city, provinces, countries etc., then we prefer fixed effect model as a reasonable choice. So, for the cross sectional units like cities, provinces, countries etc., we prefer fixed effect model as a reasonable choice. Now, come to the method of estimation of the panel data. Now, consider the case where YIT is the value of a scalar dependent variable for the ith individual unit for the tth time point and xit as x1 it, x2 it plus xk it is a k vector of observed values of k explanatory variable with ith individual unit for the ith time point. Epsilon it is a scalar random distribution term. The most general model of the data model specification is YIT equal to alpha IT plus xi prime beta IT plus epsilon IT, I running from 1 to n and t running from 1 to t, where alpha IT and beta IT are the time dependent regression model parameters. And note that the model has NT plus KNT regression model parameters which cannot be estimated on the basis of NT sample observation without imposing parametric restriction. So, what basically we need some parametric restriction in order to have a consistent estimate of the parameter. Now, consider the pool model YIT equal to alpha plus xit prime beta plus epsilon it, I running from 1 to n and t running from 1 to t, where alpha is a scalar parameter and beta equal to beta 1, beta 2 up to beta k is the k vector of slope coefficient. If for a given panel data set this is the correct specification and x's are uncorrelated with epsilon it, the model will be consistently estimated by OLS. However, for individual I, epsilon it is likely to be autocorrelated and or heteroscedastic and hence pooled OLS may not be the efficient method and also it will underestimate the standard error of the estimated beta. Now, let us consider the model with unit and time dummies. So, introducing unit dummy and time dummy for each of these observations, we have a composite model and this model constitute n plus t minus 1 plus k number of parameters and this can be estimated if both n and t tending to infinity. Now, but for the short panel as n tends to infinity and t finite, the t minus 1 gammas can be consistently estimated. Now, the question arises whether beta can be consistently estimated. Now, as n tends to infinity, number of parameters to be estimated increases and hence the question of consistent estimation of beta rises. Now, note that if the individual units can be grouped into a fixed number of a subgroup based on some criteria, then the problem mentioned above may be resolved and beta can be consistently estimated. So, if one can group the observation into some different subgroup based on some definite criteria, then problem of estimation as mentioned above can be resolved and one can get consistent estimate of beta. So, let us distinguish between the fixed effect and random effect model. Now, allowing for individual specific effect, we have the model yit equal to alpha plus xit prime beta plus epsilon it. Epsilon it are independently and identically distributed over I and t. Here alpha is a random variable that captures the unobserved heterogeneity, and the following assumption of strong exogeneity is made. Epsilon it given alpha it and xit equal to 0. Note that strong exogeneity rule out the presence of lag dependent variable in the set of exploratory variables. Okay. So, by assumption of strong exogeneity, we rule out the existence of lag dependent variable from the set of exploratory variable. Now, consider the fixed effect model. This allows the individual specific unobservable variable to be potentially correlated with some of the exploratory variable. Note, if fixed effect alpha 1, alpha 2, alpha n are present and correlated with xit, then pooled OLS estimator of beta will be inconsistent, and therefore, an alternative consistent estimator of beta for the fixed effect model is called for. Now, an alternative fixed effect estimator, that is the first difference estimator. Given the fixed effect estimator of the model, we can have first difference model taking difference of yit from yit minus 1. Note that pooled OLS on the first difference data set will yield a consistent estimator of beta. However, since epsilon it is IID, delta epsilon it will be moving average error and hence autocorrelated, and therefore, this pooled OLS first difference estimator will be inefficient and its standard error underestimated unless appropriate correlation are not done. Okay. So, you find that in this case the delta epsilon it will be moving average process and it affects the consistency property of the estimator. Now, come to the random effect model. In this model, the individual specific effect epsilon I are assumed to be distributed independently of the explanatory variable. Additionally, alpha I are assumed to be distributed identically and independently with mean alpha and variance sigma alpha square. Note that no specific form of the distribution is assumed. That is, what we are basically assuming alpha I as is coming from any random sample, but we are not assuming any specific form of the distribution. Now, let us distinguish between the fundamental difference between the fixed effect and random effect model. Now, both models are expressed as yit equal to alpha I plus xit beta plus epsilon it, so that both models assume expectation of yit given alpha I and xit equal to alpha I plus xi prime beta. The individual specific effect alpha i's are unknown and these cannot be estimated in short panel. Now, taking expectation, you get expectation of yit given xit equal to expectation of alpha I given xit plus xit prime epsilon it. Now, for the random effect model, it is assumed that expectation of alpha I given xit equal to alpha, so that expectation of yit given xit equal to alpha plus xit prime beta. Hence, it is possible to identify expectation of yit given xit. Now, for the random effect model, not only beta can be consistently estimated, it can also be identified. For the fixed effect model, on the other hand, expectation of alpha I given xit varies with xit and it is not known how it varies. Therefore, expectation of yit given xit cannot be identified. However, it is possible to consistently estimate beta in the fixed effect model even with the short period data. Now, let us consider the issue of endogeneity in the panel data analysis, and for this we perform Hushman-Taylor hybrid form of the model. Now, consider the panel model yi equal to alpha plus beta I xit plus epsilon it, or yit equal to beta xit plus vit, where vit represent the composite error ai plus epsilon it. Now, suppose the assumption covariance of xi and ei is equal to 0 does not hold, that is an endogeneity problem arises, then the random effect model is specified as the difference between yit minus lambda yit bar equal to beta xit minus lambda xi bar plus vit plus lambda vi bar. Here, Weyler's estimation of this random model will not yield consistent estimator of beta, because xit minus lambda xit and vit minus vi are assumed to be correlated. In this lecture, we basically summarizes the difference between the fixed effect model and first difference model, and then discusses the estimation of the random effect model. After that, I have discussed the test procedure which has been used in order to see whether pool model vis-a-vis the panel model is applicable, and finally, I have discussed the Hausmann specification test to see whether the random effect model or the fixed effect model will be applicable for the present scenario, and then discuss different method which has been used for estimation of the panel model.